it makes more sense to me that the compressible formulation is used. So that's what we choose. There are, in terms of grid, you can go for a relatively simple, structured, uniform, or somewhat algebraically stretched grid, versus you can explore adaptive grid refinement.
Question, does the acoustics really have an important effect on the dynamics in these calculations?
No, what I'm saying is the chemical timescale is so short.
No, but that's not the question. Does the acoustics play an important role? Because you could have done incompressible gas dynamics.
Well, in the subsonic combustion, except for those possible acoustic instability.
That's what I'm asking. Is there any evidence of that happening in these calculations? Or?
Not this type of things. There are certain scenarios where, like real gas turbine devices, where the acoustic, the bouncing can affect the combustion behavior, but not in this type of simulation. Adaptive grid refinement is probably more adequate when you have certain specific region within your domain where you need fine resolution, such as flame propagation in a channel, so you don't have to grid up the entire domain. Most of our application so far has been just like you saw in the earlier images. The small scales are widespread throughout your entire domain, so it makes more sense to just simplify your grid structure, either uniform or slightly algebraically stretched, and that's the choice we made. Spatial differencing and time integration, we use a high order versus low order. One might argue that why not use a fine resolution and keep the low order, because it's easier to implement. And I'll have an explanation why we want to do it that way in the next slide. Because the answer is that high order method is eventually will become more efficient in terms of calculation time when the accuracy is really, really important. Spatial differencing can also be done. Some of the earlier generation of these DNS code utilize the so-called compact implicit derivative scheme, which is also called the Padé scheme. Because of the reason that I'm going to show in the next slide again, we decided to go for an explicit scheme because it's easier to implement, especially in the NPI context. If you have to invert the matrix, it's a little bit more complicated when you want to decompose a domain. Time integration, again, when you have such a fast timescale chemistry, why not utilize implicit time integration? This is a good question, and we have actually tried to do it for a long time. But implicit time integration gets also expensive. You have to compute all those Jacobians every time step. Instead, we've been getting a lot of help from those the other computational tool to have the reduction of the mechanism. On top of that, we are utilizing all this quasi-steady state approximation and computational singular perturbation analysis to remove those temporal stiffness. So basically, time scale disparity in your chemical reactions are much smaller, so that we can still step it at the reasonable time scale that is physically relevant, so it is no longer a stiff system, so we can still enjoy the simple explicit time integration. This explains why we want to go for a higher order method. I don't know how many of you are familiar with this plot. This is a standard modified wave number diagram. This is non-dimensional wave number of your feature. This is a physical wave number. This is a numerical image. If that's a 45 degrees straight line, that means it's perfect, which happens with your spectral code. All finite difference code is not perfect. They can catch up with up to a certain wave number and they fall off. So the longer you maintain on this line, the more accurate. So as you can see, those E stands for explicit scheme, T stands for tridiagonal Padé scheme. So what we are using, so 6T is a kind of typical compact scheme they used to have at Stanford group in their DNS, which is shown in the purple line, I believe that, yeah, 6T is right there. 8E is our red. So it is slightly worse than the 6T, but again, in favor of its simplicity for parallelization, we opted for 8th order explicit finite difference, and we've been keeping that way. So what I was also going to show you here is a high order, 8th order scheme compared to second order, which is kind of typical commercial code. The accuracy is preserved at much higher wave number, meaning you can afford to have a much bigger grid size for the same level of accuracy, which is really critical when you really have to have multidimensional simulation with the millions of grid points. The 1 million versus 5 million, 4 million grid points, it's a matter of 1 week to 3 months. So that really counts a lot. Same thing can be said about time integration. Higher order time, this is the different types of longitudinal scheme from 5th order, 6th order, 8th order. You don't have to pay attention to other small numbers here. It just goes to show you that and this is a global error. So meaning the lower you go, it is a really tight error tolerance. So if the accuracy is really important, like in your DNS simulation case, you're about here, and clearly higher order method takes up less number of function evaluation, meaning it's less expensive. So you don't necessarily have to use higher order method all the time. If you are only interested in fairly crude solutions way up there, low order might be just fine. But if you really have to ensure high accuracy, higher order method ends up being, despite the fact that it involves more function manipulation per node, it still is less expensive. That's kind of a take-home message and general basic principles about safety. All right, so let me switch gear to research highlights. I would like to give you just a couple of key subjects. Actually, 3 I selected. I don't know how much time I left. So this second bullet item is the one that I covered last October, so I'm going to skip that part. Today, I would like to talk a little bit about computational aspects, which I feel kind of a little bit proud of, that I resolved this issue. This was a long-standing problem about reacting flow simulation. So I'm going to briefly talk about that. And then the mixing model development, which is a kind of one example of how we develop device-level subgrid combustion model based on DNS database. And that's a good example. And the final subject, given time permitting, I'm going to talk about soot formation dynamics in turbulent flames, and then and that's the story. The flame spray interaction, and these are presented last time, so I'm going to skip that part. So characteristic boundary condition. For the compressible flow, the compressible formulation, since you have to deal with acoustics all the time, the boundary treatment is really critical. Well, this is especially so in a big simulation case. You cannot afford to take your boundary, the domain size large enough that there's nothing happening there. Almost all the time you have to end up cutting off your domain in the middle of action. So the flames passing through, vortex passing through. So how do you deal with that? If you don't do it carefully, there's spurious acoustic flow, the wave reflection that contaminates the whole solution field. So this has been a long-standing question. It's actually aeroacoustics community has been working a lot into that direction, although they really didn't care much about reacting flow. So combustion community has borrowed all the knowledge from there, and it never worked. It's always been a problem. Whenever the flames start to approach the boundary, and it just code crashes. So we made some effort, and we found this is one thing I liked about this project, this discovery was that it was so easy after you learned about it. So I was really kind of really happy to figure that out. Let me see. Oh, I moved fast. Okay. So the characteristic boundary condition, again, like I said, historically the main driver was in the aeroacoustics community. And in the case of the reacting flow conditions, the Poinsot and Lelle back in 1992 was a kind of a standard back then when I started working on that. But still, all this proper handling was still lacking. So when they try to apply it to the real turbulent reacting flows where intense actions are going on near the boundary, all sorts of bad things are happening. The thing is, the whole thing is about characteristic wave analysis. You know, all this